OK, so in this example, ladies and gentlemen, I think the best thing I want you guys to do is draw your two vectors. All right? And when you're drawing your vectors, you can label your vectors any way that you want to. But whenever we're talking about bearings or compass readings, the main important thing, guys, I think is drawing some navigation. North, east, south, west. Give us somewhere where we understand where we're at and what we're doing. OK? Now, the next thing that we're going to need to know, what are you writing there? Oh, well, you don't need that on your phone. You can actually turn that off for now. So we have a ship is heading due north at 10 miles per hour. So I'm just going to draw a nice little vector. Now, again, we're going to say from some position. And then I'm going to call that S, because I'm going to represent that as ship. If you don't want to call it S, you want to call it X, Y, U, V, W. Those are all perfectly fine. OK, Laura? All right. The next one is we have the current is flowing at 3 miles per hour. So I'm just going to use a different color for my purposes. And that is at a mile per hour at 225 degrees. So from here to here is 90. Here's 180. 225 then is going to be halfway between 180 and 270. It's actually like 45 degrees is the reference angle. And I am going to call this C. OK? Now, at this one, we know that this angle here, or to the miles per hour, this is 10 miles per hour. And this is 3 miles per hour. Would you guys agree with me? Yes? OK. Now, if you haven't been in a ship or a boat, maybe you guys have at least been in, hopefully, in a car. Now, and I know in the state that we live in, we don't have many of these. But when you're going up a hill, if you have your gas on the accelerator, and you're going 60 miles per hour, and then you start going up a hill, unless you press harder on that accelerator, you are going to slow down, because then you're going against the force, gravity, and all these other forces that as far as going up the incline. Okay? So this boat is traveling. And what we have is we have this current, which is going against the current, which I would just say is kind of like in a car. It's like going up a hill. You have these new forces that are acting against you. That's pushing the boat basically to the left, due west, and back. OK? So we know, if we think about this, it's going to be taken, unless we correct it, which we're not correcting it. If we're not correcting it, we know our final angle, what they're asking us, your final speed and bearing, is going to be a little bit farther over to the left from due north, right? And it's going to be a little bit slower. Would everybody agree? I'm just using estimation right now. Would everybody agree with me on that? Yes? So basically what we're looking for is we're looking for the resultant vector. What is the resultant vector of these two forces being acted on one another? And if you guys remember from last class period, we talked about how to find this by using vector addition. So what I can do is I can use my tail to end method to kind of take this vector and put it at the top there, because basically what I am looking for is this. That is my resultant vector. Right? That is the resultant of both forces being acted on one another. Now, how do we find my components of this resultant vector? Well, they're looking for the final speed. So we need to find the magnitude of that vector. But before we find that, we need to find the components, right? So let's talk about vector S. Vector X, I think, is pretty simple. You're not going left or right, so that's 0. And again, we're just talking about speed at this point in time. So we're not talking about how long they've traveled and so forth. So we're dealing with 10 miles per hour, which I'm just going to use as writing as 10. So that would be the component form of this vector. Would you guys kind of agree based on the information we have? No? Yes? So then my other vector, which would be C, now I don't have any components. The only thing I have is 3 miles per hour. But I do have a what? I do have what? Angle for it, right? So if you guys can remember, there was those 3 forms that we talked about how to write a vector. For C, I can write a vector based on its magnitude, or what I would, I can, based on its magnitude, times the component form of it, or the angle, which is cosine of 225 degrees, comma, sine of 225 degrees. If you guys remember, magnitude, cosine of theta, sine of theta, that was in your notes last class period. The magnitude of a vector times the cosine of the angle times the sine of the angle. That was in our notes from last class period. So really what we want to do is find s plus c. What is s plus this vector? What is that resultant vector? Anyways, let's see what this is. So therefore, I'm going to need use my calculator. Now again, this is in degrees, so if you have your calculator, you got to go back out from radian mode and into degree mode, right? So here I'm just going to do cosine of 225 times 3. And I get negative 2.121, comma, and then sine of 225 times 3. So then if I do s plus c, I am going to be left with a negative 2.121, comma, 7.877, as I'm rounding to the nearest thousandth. You'd want to be careful. Usually on this, I tell you guys not to round until the very, very end. So you could definitely go ahead and store these. I'm going to have you guys be rounding to the nearest, to the actual speed on this. But if we were looking into getting something rounded, yes? What? I added the terms, added those two, which is obviously 0 plus that, and then I added these two. Because remember, vector addition, you add the first components and you add the second components, right? Good. Thank you for making me clarify, though. So now, yes? I don't know. What did I? 7.879, yes. Thank you. And what did I call s plus c? I'm calling this what? R, right? So R is my resultant vector, which is that. Okay? Now, what are they asking? They're asking for our direction. They're asking us for the direction as well as the magnitude. So to find the magnitude, or the speed, I'm just going to find the magnitude of this. So the magnitude is basically going to be, if you guys remember from your formulas, the square root of r1 squared plus r2 squared. It's basically your first component. When you have it in component form, it's pretty simple. It's the square root of your first component squared plus your second component squared. So when you're typing this in your calculator, just make sure, guys, you're using parentheses. I made a mistake in a class because I was talking and I forgot to plug in the parentheses. Because if you don't put parentheses around that negative, it's not going to square the negative and make it positive. It's only going to square the number. So we really got to make sure that you have that in parentheses. So type it in just like I have it as far as the square root. Open parentheses, negative 2.12, and parentheses squared, plus open parentheses 7.879, close parentheses squared. And I'm getting a magnitude, which I'm rounding to the nearest whole. I don't think I told you guys that. I'm rounding to the nearest mile per hour on this. So magnitude of R is going to be 8 miles per hour. Since I originally, my problem was based on the premise of rounding this. That's why I'm not using these whole answers. However, guys, again, if this was like a problem, and if it was something very particular, like very detailed, you wouldn't want to be rounding this in there, okay? You'd want to make sure you're very, very detailed using the exact answers. So you'd want to store them in your calculator. But for time purposes, we're using a rough result. All right, now does that kind of make sense? 8 miles per hour. You're going 10 miles per hour, and you have this current going against you. Now you're only traveling 8 miles per hour. Does that make sense in the context of the problem? Yes. We know something would probably be wrong if you were like at 2 miles per hour, right? Or if you were at 70 miles per hour. Uh-oh, I did something wrong, correct? So make sure you guys, your answer is in the context of the problem. Now the next thing is we need to find the angle. Remember, the angle tangent of theta is equal to r2 over r1. Basically, your second component divided by your first component. So I could say theta is equal to tangent inverse of r2, which is 7.879, divided by negative 2.121. And I didn't write it up there, but I wanted you to round to the nearest whole degree. So once we get our answer, we're just going to round it to the nearest whole degree. So I'll just type in inverse tangent, and I'll type in 7.879 divided by negative 2.121. And it looks like I'm getting negative 75 degrees when I round it. OK. Justin. Really need to make sure you're paying attention to this, because this is really important, because this is going to show up on your quiz. This is going to show up on your quiz. Everybody needs to make sure that you are aware of this, because so many people are going to make this mistake. So again, in the context of the problem, they're asking us, first of all, for the bearing. But remember, your calculator doesn't care about bearings, right? You need to understand what the bearing is. Your calculator is going to give you angles in standard position. And not only that, your calculator, remember tangent, sine, and cosine have restricted inverse domains? Their domains are restricted? Yes? So when you're doing the inverse tangent, you're only going to get an angle from here in the first and the fourth quadrants. That's what your only angle is going to be, is in the first and the fourth quadrants. So what I'm trying to tell you is, do not just rubber stamp whatever's in your calculator and say, oh, that's my answer, right? Because you will get a problem wrong in your test and quiz. Anyways, this is negative 75 degrees. We know here's our vector. That's why I told you guys to graph this. Negative 75 degrees is like somewhere over here. Correct? You guys agree with me? Yes? And the reason why is, remember, your calculator is only going to give you angles in the first and the fourth quadrant. But in reality, what we found, what we plugged in, was that angle right there, which is the same as that angle. Oh, I'm sorry. Same as this one. Those two angles are the same as far as value goes. But your calculator is only going to give you the negative value of this. So in reality, that value is 75 degrees. These two angles are the same, but your calculator is only going to give you this answer because your domain is restricted on the inverse tangent. However, so now let's go and take a look at what we're going to do. If we want to find the bearing, we want to find the angle from due north, right? So let's just count. 90, 180, 270, and then how much farther do I need to get to go over there? So I'm at 270, and then I need to go an extra 75 degrees. So that would be 345. So the angle, and what you'd write is you'd write bearing of 345 degrees. And does that sound about right, right? Yeah, that looks about that right angle, because bearing is from due north. Correct? So I'm just telling you guys, you're going to have to adjust from what your calculator tells you. Yes?
Could I say negative?
Well, that's why we're asking you for what the bearing is. You mean like, could you do it from due north? Yeah, you could also say due north. There's another way of writing it, which would be fine for bearing. So you could also say north 15 degrees west, right? Yeah. That's another way of writing it from there as well. OK? Anybody